everyone. Today we're going to talk about two very important, very critical theorems in calculus. The first is called the intermediate value theorem, and the second is the mean value theorem. Okay, first of all, the intermediate value theorem. If function f is continuous on a closed interval ab, so that's crucial first of all. It has to be a continuous function. Then f takes on every value between f of a and f of b on the interval a to b. If function f is continuous on a closed interval ab and k is between f of a and f of b, then there is at least one c in ab such that f of c is equal to k. Okay, what is this all about? Well, if I were to tell you that I knew, for example, that f of 1 was equal to 3. So 1, 3 was on my graph. And I was also going to tell you that I knew that f of 5 was equal to 8. So 5, 8 is also on my graph. And I'm told that it's a continuous graph. Well, clearly we don't know what happens if we're only given those 2 points. I don't know what happens between the 0.13 and the 0.58. The graph could do anything, but I know it has to start here and end here. And it has to be continuous. So it could go like that. Well, it couldn't. It has to be a function, so it could do all sorts of things. Okay? But we know that eventually it has to get there. So what it's saying is any value between 3 and 8, any y value between 3 and 8 will eventually be reached, because any value here is eventually going to be reached no matter what, no matter how the function gets drawn. So this is saying that there is some value c between 1 and 5 such that f of c will equal wherever my k is. The table below shows several measurements of the velocity of a bicycle riding on a straight road. V of t is continuous on the interval 0 to 20. Okay, so you can see the table is giving you different times, and the outputs are the velocity. So it says for 0 to 20, must there be a time t when v of t equals 2.5? Justify your answer. Okay, so we really want to look at our outputs here. And we want to say, what are our y values and what's happening? So you can see here our y values. Okay, we start off at 3.3 when the time is 0. Then after 5 seconds, we've gone to a velocity of 4.2. Now we don't know what happened between the 3.3 and 4.2. We could assume that it just continued to increase. We could assume that it went down and then up. We don't know exactly what happened, so we cannot be confident that 2.5 falls in between there. Okay? Then it went from the next 2 seconds, it went down to 2.7. Now again, it could have dipped below 2.7 and then come back up, but that we cannot be sure there. Here, 2.7 to 2.3. Okay, now if I start at 2.7 after 7 seconds and then 2 seconds later I'm at 2.3, I have to have reached every height, every velocity between 2.7 and 2.3. So we can go ahead and conclude that yes, and to justify that we say v of 7 is greater than 2.5, which is greater than v of 9. And then we say by IVT. All right, intermediate value theorem. So what this is doing is it's giving us the two x values that bookend, if you will, the two y values where the 2.5 falls in between. So this is saying 2.5 falls in between the output for 7 and the output for 9, telling me that there must be a time t between 7 and 9 such that 2.5 is an output between v of 7 and v of 9. All right, so let's look at the next question. For 0 to 20, must there be a time t when v of t is 5. Okay, so now look, basically what we're looking for is 5 to have to fall in between two of our values. So if I look here, 3.3 to 4.2, 2.7, 2.3, 3.8, 4.6. 5 does not fall between any of those. So we would conclude that no, there are no v of t values with a 5 in between. Okay, what is the least number of times where v of t is exactly 4 meters per second? So what is the least number of times that we are going to for sure reach a velocity of 4 meters per second? All right, so if I look here, I have to find every time where there is two velocity outputs that have a 4 in between them. So how many times does that happen? Well, I would say right here it happens once, okay? And then from 4.2 down to 2.7, it's going to happen again. 2.7 to 2.3, no. 2.3 to 3.8, no. 3.8 to 4.6, yes. So I would definitely say that there are 3 places where 4 fits in between the two outputs in the different intervals. So I would say that 3, because f of 0, or v of 0, sorry, is less than 4, which is less than v of 5. V of 5 this time is greater than 4, which is greater than v of 7. And then the last one, v of 14, is less than 4, which is less than v of 20. Okay, so now for the mean value theorem. The mean value theorem is mentioned quite a few times in the AP exam, and they really want to make sure you understand this concept. So the first big thing about it is there are 2 conditions in order for the mean value theorem to even hold for a function. First of all, the function has to be continuous on a closed interval a to b, and second of all, it has to be differentiable on an open interval a to b. All right, if those 2 conditions are met, then there exists at least one value c within AB, and notice that's a open interval again, so that means that it can't be A or B, such that f prime of c is equal to f of b minus f of a over b minus a. All right, so let's take a look at this formula for a second and just kind of break it down. All right, what does f prime of c hopefully remind you? All right, first of all, that should be your instantaneous rate of change, your IROC. That, remember, is the derivative, all right, and that, of course, is your slope of your tangent line. And where is that tangent line? Well, it's the tangent line drawn at C. Okay, so that's what the left-hand part of this equation is. What is the right-hand side of the equation? Well, the right-hand side of the equation is your average rate of change, your AROC. And what is an AROC? It's the slope of the secant line between or connecting f of a and f of b. Okay, so here is my secant line that they have drawn in right here. Okay, so they are saying, this theorem tells me that as long as this function is continuous and differentiable between a and b, then there must be a point such that there is going to be a tangent line that can be drawn with the same slope, drawn to that function at a certain value c, with the same slope as that secant line. So you can kind of visualize this. I could draw in, okay, I need to maintain this exact same slope, but I need to draw it so that it's tangent to this curve. So hopefully you can visualize that that is possible right here. All right, so I'm going to go ahead and kind of sketch that in the best I can. Oh, that was bad. Let's try that again. Get a little closer. Okay, so there is my tangent line to this graph, to this function, at some value c. C is between a and b. This tangent line is the same slope as the secant line. Okay, so what we do generally with these problems is we find the value of c that maintains or that holds on to the mean value theorem, or that proves the mean value theorem. Okay, this next set of questions asks us to do two things. First of all, we have to determine if the mean value theorem applies to the function on the given interval. And then, if so, find all values of C that guarantee the theorem, that are guaranteed by the theorem. So what does this mean? How would we know if the mean value theorem applies to the function? Well, we have to answer two questions. First, is the function continuous over the interval a to b? And second, is the function differentiable over the interval a to b? Now notice the difference in those markings. Continuous is over the closed interval a to b. Differentiable is over in the open interval a to b. All right, so let's look at our first example. It says we have f of x equals 4x squared minus 20x plus 9 on the closed interval 1 to 4. All right, so when we're looking at this problem, we have to answer, is it continuous, is it differentiable? So first of all, this is a polynomial function. When we have a polynomial function, we know that the domain, the x values that I'm allowed to put in, which would make it continuous, would be all real numbers. It is a continuous function no matter what x's you put in. Okay, is it differentiable? Well, yes, if I take the derivative of a polynomial function, I get another polynomial function, I'm all set. So I would definitely say that yes, it meets both of those criteria, and the mean value theorem does apply to this function. Okay, so now I've answered those questions, I can move on to actually finding the values of C guaranteed by the theorem. So there's nothing tricky with this one. All right, so that means I need to actually use the mean value theorem. I need to write that down. So the mean value theorem says f prime of C has to equal f of B minus f of A all over B minus A. Okay, so now I'm going to go ahead and kind of do each of these pieces one at a time. So first of all, f prime of C. Well, in order to find f prime of C, I need to first of all take the derivative of f. So f prime of x is equal to 8x minus 20. Okay, so that's the derivative at x. If I want the derivative at c, I'm just replacing my x with a c. So 8c minus 20 is equal to. All right, now the right-hand side is the average rate of change. I'm using the original function, and I'm finding f of b minus f of a over b minus a. Where is that function? Where are those b and a coming from? They are coming from the interval a comma b. And so I know that I have to find what f of 4 is and what f of 1 is. So I'm kind of going to do it off to the side. All right, so f of 4 here would be 4 times 4 squared, so 4 times 16, which would be 64, minus 20 times 4 is 80, plus 9. 64 minus 80 is negative 16, plus 9 is negative 7. All right, f of 1, 4 times 1, 4, minus 20, plus 9. 4 minus 20 is again negative 16, plus 9 is again negative 7. So plugging that in, all right, f of 4 would be negative 7 minus a negative 7 all over b minus a would be 4 minus 1. So I get 8c minus 20 equals, if I clean this up, negative 7 minus a negative 7 is 0 over 3. So that's obviously just going to be one big 0, okay? So I'm going to add the 20 over, 8c is equal to 20, and c is equal to 20/8. Or, of course, if I divide top and bottom by 4, I get 5/2. So that is the C value that falls, and I always want to make sure, does that C value fall in this interval? Okay, inside it, it can't be 1 or 4. It has to fall inside of it. So 5/2, 2.5, does fall in between 1 and 4. And what that's saying is that the slope at C of the tangent line at 5/2 is equal to the average rate of change between 1 and 4. Okay, the second one here, f of x is equal to 4 plus the square root of x minus 1. All right, so again, we have a radical this time, and so we're looking over the interval 1 to 5, and we're asking ourselves, is it continuous, is it differentiable? Well, radical functions are a little bit trickier, okay? So to answer the question, is it continuous, I have to make sure that every value in my interval, when plugged in, does not make a negative number under the radical, basically. So when I'm answering this question, I have to kind of look at what is the domain of this function. And so I have to say that the numbers under the radical have to be greater than or equal to 0. So x would have to be greater than or equal to 1. And clearly the numbers in this interval, 1 to 5, and remember it has to be continuous on the closed interval 1 to 5. And I would say yes, it's continuous over that closed interval because of the domain as x is greater than or equal to 1. So we're going to say yes, it is continuous over that closed interval. Is it differentiable? Now this time it's over the open interval 1 to 5. All right, so now I have to figure out if it's differentiable. Well, how do I do that? I take the derivative. All right, so I'm going to rewrite f of x as 4 plus x plus 1 to the 1/2. And now when I take the derivative, obviously the derivative of 4 is gone, and then move my half in front, x plus 1 to the negative 1/2, and then the square root of, or the derivative of x is 1, so I don't have to put anything. All right, so if I clean that up so I can make it look like a fraction here, I have 1 over 2 times the square root of x. This should be minus 1. I don't know why I did that. Okay, so if I take a look at this, all right, now what is different about this than the original? Well, now my radical's in the bottom. So I have to have positive numbers under the radical, and I cannot have a 0. So now my domain for this, all right, would be that x minus 1 would have to be greater than 0. It couldn't equal 0 because then I'd have a 0 in the denominator. So x would have to be greater than 1. And that's why it's so important to keep in mind this open interval right here. All right, is it differentiable? Over the open interval 1 to 5. So notice that in this open interval, 1 is not included. So yes, this is still okay because it is differentiable in the open interval from 1 to 5. And so that's fine, and it checks out. All right, so now it's continuous and differentiable, and so therefore I would say the mean value theorem does apply to this. Okay, so mean value theorem applies because we were able to answer these two questions. Now we're going to go ahead and actually find the value of c that is guaranteed by the mean value theorem. So how do I do that? Well, I write down my formula. F prime of c is equal to f of b minus f of a all over b minus a. Okay? You already found the derivative right here. You're going to take that but replace the x with a c. So 1 over 2 times the square root of c minus 1 is equal to, all right, so now I need to do f of b. So that would be f of 5 here is equal to 4 plus the square root of 4, which is 2, so 6. And f of 1 would be 4 plus the square root of 0 is 0, so 4. So I'm going to go ahead and say that's 6 minus 4 over 5 minus 1. So I have 1 over 2 square root c minus 1 is equal to 2 over 4, or 1/2. Okay, I can go ahead and cross multiply here. So I would get 4 square root c minus 1 is equal to 4. Divide both sides by 4, you get square root of c minus 1 is equal to 1. I'm going to go ahead and square both sides. So c minus 1 is equal to 1. Add the 1 over, c is equal to 2. Okay, does 2 fit in between 1 and 5? It sure does. And so c is equal to 2 is the value guaranteed by the mean value theorem. Okay, so taking a look at this third one, it's a rational function, and we want to be really careful with our domain for rational functions. So f of x equals x plus 3 over x minus 2. The question is, okay, what is the domain here? What's allowed? What x values are allowed? Well, we know right away that x cannot equal 2. And we know that when x does equal 2, we're going to have a vertical asymptote, which would clearly make it not continuous. So does the value x equal 2 fall within that interval? Yes, it does. And so right away we would say that this is not continuous over negative 2 to 3, and therefore mean value theorem does not apply. Okay, so we can't go any further. We can't use the mean value theorem because the mean value theorem is not applied in this given interval. Okay, so we're going to do one more example of this type. And again, we're given a polynomial function. So polynomial functions, like I said, nice and easy. Yes, it's going to be continuous over this. Yes, it's differentiable. Okay, so it does, the mean value theorem applies. All right, so now we're going to move on, and we're going to go ahead and write down the mean value theorem. So f prime of c is equal to f of b minus f of a over b minus a. All right, so we need the derivative of this function. So f prime of x, off to the side here, I'm just going to do that, 3x squared minus 1. Okay, so I'm going to plug that into my formula with a c. So 3c squared minus 1 is equal to. All right, now let's figure out f of b. So in this case, remember your a and your b are right up here, a and b. So it would be f of 2 would equal 2 cubed would be 8, minus 2 would be 6, and f of 0 would be 0. All right, and so I'm going to go ahead and plug those in. So I would have 6 minus 0 over 2 minus 0. And so I get 3c squared minus 1 is equal to 6 over 2 would be 3. So 3c squared is equal to 4. C squared is equal to 4/3. Okay, so c is equal to, now remember when you take the square root within an equation, it's plus or minus the square root of 4/3, which is the same as the plus or minus 2 over square root 3. Okay, so remember that's two different numbers. That's 2 over the square root of 3, and that's negative 2 over the square root of 3. I have to ask myself, do both of those fit within the given interval? Well, my given interval was from 0 to 2, so clearly the second one, the negative one, is rejected. Okay, because it's negative. It's not within that interval. All right, now the first one, 2 over radical 3, does that fit? Well, square root of 3 is about 1.7. 2 divided by 1.7, yes, that would fall between 0 and 2. So this one we would go ahead and accept. Okay, number 5 says v of t is a differential function and has the values given in the table below. Letter A says, must there exist a value t equals c in the interval 20 to 44 such that v prime of c is equal to 1/3? Justify your answer. All right, so does there have to be a value between there such that v prime of c is 1/3? So they are giving you this time the instantaneous rate of change, and they're asking you, does that hold true in this given interval? All right, so remember your mean value theorem says, all right, f prime of c has to equal f of b minus f of a over b minus a. So I'm just using that formula with this given interval, okay? And they told me v prime of c, in this case, I'd be using v, not f, is 1/3. So they're giving me the 1/3. Does that equal? Well, f of b here, okay, v, these should be v's. All right, so v of 44 is 18 minus v of 20 is 8 over 44 minus 20. So I have 1/3. Does that equal 10 over 44 minus 20 is clearly 24. And so even if I simplify this, 10 over 24 certainly does not simplify down to 1/3. So my conclusion would be no. And really my justification is the work that I did mathematically, showing that there is not, and the average rate of change does not equal 1/3. All right, letter B, same kind of idea. Must there exist a value t equals c in 44 to 80? So this time I'm looking at these 2 points, okay? So over this whole interval, such that v prime of c equals negative 1/6. So same thing, v prime of c equals v of b minus v of a all over b minus a. And this is really a question I'm asking, is this true? So v prime of c is equal to negative 1/6. So what is the average rate of change over the course of those 2 points? So I would say v of 80 would be 12 minus v of 44 is 18 all over 80 minus 44. Okay, so that would be negative 1/6. Does that equal, this is negative 6 over 36, which clearly, yes. Those fractions are equal, and so therefore there must exist a value of t equals c in between there, where the instantaneous rate of change is equal to the average rate of change. Okay, last example we're going to do. The function f is continuous from negative 5 to 1, and f of negative 5 is negative 2, and f of 1 is 4. Which of the following statements must be true? More than one or none could be true. Okay, these are very popular questions on the AP exam where they give you these choices and you have to figure it out. And oftentimes it's using either the intermediate value theorem or the mean value theorem. So first thing I would do is just kind of make a sketch of what did they give me. All right, they gave me 2 points here. F of -5 is -2. So that is the point, of course, -5, -2. They also told me f of 1 is 4. So 1, 4. All right, so I'm just kind of, like I said, make a sketch giving this information. Okay, so one of my points is right here, and the other point is right here. Okay, so this goes back to what we talked about at the very beginning, the intermediate value theorem. All right, look at this first question here. It says there is at least one C in between, where C has to be between -5 and 1, such that f of C, such as the output, the height, is going to equal 0. Well, where is 0 on this graph? Well, obviously, hopefully you realize that's the x-axis. Okay, so does 0 fall in between -2 and +4? Absolutely. And so no matter how I connect these two dots, as long as it's a function, I have to pass through the x-axis. Therefore, okay, as long as it tells me it's continuous and it's a function, then it's going to have to pass through the x-axis. And so I would say that number 1 is a yes by the intermediate value theorem. Okay, number 2. This says there is at least one C between -5 and 1 such that f prime of C is equal to 0. Well, what does it mean if f prime of C is equal to 0? What does this mean? It means the derivative is equal to 0. What happens if the derivative at C is equal to 0? Well, that would mean that you would have a horizontal tangent. Okay, is it guaranteed that I'm going to have a horizontal tangent? In other words, will I have a relative min or a relative max? There is no guarantee. Remember, I could draw this any which way. So yes, I could draw it so that it came down like this and there was a horizontal tangent. Okay, I could draw it so it came up like this and there was a relative maximum. But I could also draw a straight line. And if I drew a straight line here, then there would absolutely be no horizontal tangent. So I would say that definitely number 2 is a no. Okay, last one, the function f has an absolute maximum value from -5 to 1. Okay, so this is the closed interval theorem. All right, this told us way back, we learned about absolute maximums, that anytime you are given a closed interval, okay, so from -5 to 1, and the function is continuous, there is going to be an absolute min and an absolute maximum. So yes, number 3 is true. So you would say, which of the following statements are true? I would definitely say 1 and 3. All right, that is it for tonight. I hope you have a great night, and I will see you tomorrow.